Okay. As we missed a day for Thanksgiving, we're a little behind, which is why I keep postponing homework 12. So I thought I would cover the basic material that you need to know to finish homework 12 on video, seeing as that worked so well when I was in Prague. So what we're going to do now is, at the end of last class, I introduced the one extra rule of equivalence for predicate logic, which was quantifier negation, also known as magic hopping tilde. And that's the only extra rule of equivalence. Now remember, rules of equivalence are different from inference forms. Rules of equivalence can apply to parts of lines. So anywhere there is a tilde next to a quantifier, anywhere in a line, you can do quantifier negation. You just move the tilde to the other side of the quantifier, and the quantifier changes. That's the only change. Everything else in the line stays the same. That's because quantifier negation is a rule of equivalence. But what we're going to introduce now is the 4 new inference forms. So if you remember, there are 9 inference forms in non-predicate logic, and also in predicate logic, because predicate logic has everything that non-predicate logic has plus predicates. So you already know 9 inference forms: modus ponens, modus tollens, simplification, addition, all those guys. Okay, well now you're going to learn 4 more. Why do you need 4 more for predicate logic? The answer is because of the predicate. No, because of the quantifiers, actually, not because of the predicates. The predicates don't really make any difference. If you didn't have any quantifiers, in fact, if you have some predicate logic that doesn't have quantifiers in it, just predicates and names, then you don't need any of the new rules. You don't need quantifier negation because there's no quantifiers, and you don't need any of the 4 rules that you're about to learn. So it's only to deal with quantifiers. That's the only reason you need these 4 rules. And in fact, in an argument that I've used as an example many times, that kind of shows why we need quantifier negation. And that is, all frogs are green. Kermit is a frog, therefore Kermit is green. Which looks like this. Okay, all frogs are green. That's an A type, so universal quantifier, conditional. Kermit is green, is a frog. Conclusion: Kermit is green. Now, as we were saying last time, we can't just do modus ponens here because that quantifier is the main connective. You could do modus ponens if that quantifier wasn't there, and if this was not an X, it was a K. But this is an X and this is a K. So there's 2 reasons you can't do modus ponens. So what you need to do is you need something that will get rid of this quantifier so that what's left is a conditional, and that will change the X's into K's. What that thing is, as we'll see first, is something called universal instantiation. But let's take a step back. Here are, let's see. Here are, should have planned this better. High-tech stuff here. Here are the 4 new rules. They are universal or existential instantiation or generalization. So combine them. You have UI, which is universal instantiation. You have UG, which is universal generalization. You have EI, which is existential instantiation. And you have EG, which is existential generalization. All right. What the hell do these things mean? Well, you understand the universal and the existential. Universal means involving universal quantifiers. Existential means involving existential quantifiers. Those are the 2 types of quantifiers. So you know what those mean. What's instantiation and generalization? Well, they are respectively, instantiation means getting rid of quantifiers, and generalization means adding quantifiers. Why are they called that? Well, generalization makes sense because if you add a quantifier, you're going from the more specific, which involves names, remember names refer to specific definite things, to more general. You're making a more general claim. And this is obvious in particular if you're talking about a universal quantifier. So you would be going from Kermit is a frog to everything is a frog if you were to do universal generalization, which in fact you can't do in that instance. But if you could, that would be universal generalization. All right, so let's summarize the rules of instantiation first of all. There are two rules that apply to both kinds of instantiation, universal and existential. Turns out for universal instantiation there are only these two rules, but existential instantiation has an extra rule as well, as we'll see. Okay, instantiation. What do? Well, first of all, you remove the quantifier. Now remember, this is an inference form, so as with all inference forms, it applies to the entire line. So you can only do, and this is very important, this applies to your homework, you can only do instantiation if the main connective of the entire line is a quantifier. If, on the other hand, you have something like this, where, say, if Kermit is a frog, then something is a frog. So that says, if Kermit is a frog, then something is a frog. You cannot do instantiation to that, because the main connective on that line is the conditional. You can't do instantiation there. You can only do instantiation to something like this. Something is a green frog, because then that is the main quantifier. And then, of course, because that's an existential quantifier, you'd be doing existential instantiation. So remember that. That's very important. So you remove the main quantifier, and this is the note, must be the main connective of the entire line. If the main connective of the entire line is not a quantifier, you cannot do instantiation to that line. Can't be done. Like with simplification. Simplification is another rule of another inference form, and if a line has a conjunction in it, but it's in parentheses and it's not the main connective, then you can't do simplification. Okay, it's only if the conjunction is the main connective of the entire line. All right, so remove the main quantifier, provided there is one. Then replace all the variables that the quantifier bound. So let's say it was an x quantifier. Then you look for all the x's in the line, and you replace them with the same name. So you replace all the x's with whatever name you want. Now, if it's universal instantiation that you're doing, you can pick any name you want. You just have to use the same name for every x. So you can go A, B, 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 C, 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 whatever. Because for universal instantiation, you're going from a universal claim. You're going from something that says everything in the universe is this. So if everything in the universe is this, then you can pick any name you want. That's important. However, with existential instantiation, you can't do that, and we'll get to that in a little bit. But those are the two rules that apply to both kinds of instantiation. All right, let's look at universal instantiation as an example. Now, remember, we only need these rules because we're going to do proofs. So let's look at a proof, and it's the argument we were just talking about. All frogs are green. Kermit is a frog. I shouldn't have picked Kermit, really, because this little k, this is fk, and it looks like the fx, but they're different. Up here is an x, down here is a k, and of course this is a k as well. So all frogs are green. We symbolize as for everything in the universe, if it's frog, then it's green. That's an A type. Kermit is a frog. Conclusion, Kermit is green. Now, as we just said, we can't just do modus ponens because of this quantifier right here. What we need to do is get rid of this quantifier and change this x to a k. Well, turns out that's what universal instantiation does. So as you see on line 3, I do universal instantiation. I follow the two rules. First rule is you remove this quantifier. So I've done that. and then you replace all the x's with the same name. Now, I could pick any name I want, but of course, what I want to use is a k, because I already have a k here, and I want to be able to do modus ponens and end up with gk. So that's why I picked the name k here, but I could use any name. All right, and then finally, then I can do modus ponens and end up with the conclusion. So that's it to universal instantiation. There are only the two rules of instantiation that we've already introduced. But remember, it is an inference form, so you can only do it to an entire line, unlike quantify negation, which is an equivalence form. All right. Now, of these four, universal instantiation is probably the simplest. That's why we started with it. It makes the most sense. If you say, so if you start with everything in the universe is green, then clearly it follows validly that Kermit is green, or anything you like. You know, this cup is green. It's not, but you know, if everything in the universe was green, then it would follow validly that this cup is green. So universal instantiation makes sense as a valid inference form, which of course it is. That's what all the inference forms are, little valid arguments. All right, now the next simplest is existential generalization. And with existential generalization, basically, well, let's look at generalization in general. Here are the two rules of generalization. Remember, instantiation is called instantiation because you're moving from a general claim to a specific instance of that claim. You know when we use the phrase for instance, what we mean is, I've just given you a general rule, and now I'm going to give you an example. That's what instantiation is. You move from something general that has quantifiers in it to a specific instance. You move from everything in the universe is green to Kermit is green. So that's why that's called instantiation. Generalization, of course, is moving in the opposite direction. You start from something definite and individual, like a name, and you move to something more general, like a variable. All right, so there are two rules that apply to both the generalizations. First, now you're adding a quantifier. And remember, because it's an inference form, it has to apply to the entire line. So you add quantifier to the extreme left, and it applies to the entire line. There can't be anything to the left of it, and the scope of it has to be the entire line. And then, now that you've added a quantifier, you have to have something for it to apply to. If there's more than one name, then you can pick what name you want. So, for example, let's pick existential generalization. Suppose you have something like this. Romeo loves Juliet. That's a capital L, little r, J. Now, suppose I wanted to do existential generalization to that. I could do either this, which says something loves Juliet, or I could equally well do this, which says Romeo loves something. In other words, it doesn't matter which name I pick to generalize from. I can pick whichever one. What I cannot do is I cannot do this. I cannot replace two different names with the same variable. I can only pick one of the names to replace with the variable. So the first two are okay, but the last one is not allowed. Okay, so generalization, just to recap, you add a quantifier to the extreme left, and it applies to the entire line, and you replace all instances of one name with variable bound by the new quantifier. Okay, let's see it in action. So let's adapt my favorite argument about Kermit. And now it says, all frogs are green, Kermit is a frog, conclusion, something is green. Now, that's valid, right? Because obviously we know that if Kermit is green, Kermit is a frog, then Kermit is green. And if Kermit is green, then something is green. Existential generalization is obviously valid. If you go from Kermit is green to something is green, if Kermit is green, then it obviously follows validly that something is green. You're just being less specific. So it's clearly a valid argument. All right, so let's see how this argument would go. You would say, just like before, you would universally instantiate, and I would pick Kermit, and then you would do modus ponens again, and then finally I would use my existential generalization to move from Kermit is green to something is green. And again, with existential generalization, there are only the two rules of generalization that I've already introduced. Okay, so out of the four, the easy ones are universal instantiation and existential generalization. They don't have any extra rules. They're all just two rule things. That's my phone. Okay, okay. Where were we before I was so rudely interrupted by the phone? This is why you can't have cell phones in class. Oh, that's right. So the easy two are universal instantiation and existential generalization. Now, let's move on to existential instantiation. And we'll have a good story to tell about that in class, so that's something to look forward to. But for now, I'm just keeping it basic. What's weird about existential instantiation is it seems like there must be restrictions on it. Because what it's doing, of course, is it's going from something is, let's say, green or whatever predicate you're talking about, to a specific name. But there's obviously got to be some restrictions on that. Because suppose I were to say, something is red. That's obviously true. And then I were to say, this cup is red. Now that would be an instance of existential instantiation because I've replaced a variable, the something, with a name. The name refers to this cup. Notice how many cups I have. But while it's true that something is red, just to prove it, this proves that something is red. It is false that this cup is red. So obviously I can't just replace the variable with any name I want. That's why there has to be an extra rule. There's an extra restriction on existential instantiation. This is rule 3. The first two rules are the rules of instantiation that I've already given you. Rule 3 is existential instantiation must introduce a new name that hasn't occurred before. So notice what happens if I try to prove this argument, which is it's another variant of the ones I've been using. All frogs are green, something is a frog, therefore something is green. That is a valid argument. But look what happens if I start, as I have done before, by introducing a name. Incidentally, now I'm not talking about Kermit, so I can just use a sort of dummy name. I can introduce any name. So that it's traditional just to use A. Who or what is A, it doesn't matter. It's just a name, kind of a placeholder. All right, so all frogs are green. By universal instantiation, I say Al is a frog. If Al is a frog, then Al is green, just because Al begins with A. Now, what I obviously want to do is I want to introduce, I want to instantiate from here and then set up a modus ponens. But the trouble is, once I've introduced that name, I can't use existential instantiation to introduce A again because of this rule. Existential instantiation must introduce a new name. So if the name A has already been used, I can't use it. So I would have to say B, and then I can't do my proof. I can't do modus ponens. What this means is that existential instantiation requires strategy when you're doing a proof. There is a way to do this proof, but you just have to be a little sneaky. And the way is this. Instead of starting by doing universal instantiation, you start by doing the existential instantiation. Because if you do that first, then there's no name above it, and it's okay to use whatever name you want. And then you can do the universal instantiation, and because there are no restrictions on universal instantiation, you can match the name. So then you can use the name that you've just introduced, and then you can do modus ponens, and then you can do existential generalization, as we've learned how to do just now. So put that all together, and it would look like this. So notice, whereas before I did universal instantiation on line 3, Now I'm going to do the existential instantiation on line 3, and because the name A has not occurred anywhere above it, obviously it doesn't occur on lines 1 or 2, it's perfectly okay to use it. And then using universal instantiation on line 4, I can match A because there's no restrictions on what name you can use with universal instantiation. Alright, so just remember for existential instantiation, there is that extra rule. Universal instantiation doesn't have that rule. Only EI has that rule. Finally, we've done 3 out of 4. The last one is universal generalization. Now, universal generalization is pretty weird if you think about it. Because if you can do universal generalization, then it looks like you could start with Kermit is a frog, which is true. And then obviously universal generalization, because it's generalization, is you're going to add a quantifier. And because it's universal generalization, it would be the universal one. So you would go from Kermit is a frog to everything in the universe is a frog. Now, it's obviously true that Kermit is a frog. Well, actually, he's a Muppet, but we'll pretend. Obviously, that's true, but everything is a frog is obviously false. So, again, there must be some kinds of restrictions on what name you can do it to. And the answer is, here's the rule. Now, but you do need universal generalization. You have to be able to do it, because otherwise you couldn't prove a valid argument like this. This is our old friend. All chihuahuas are dogs. All dogs are mammals. Therefore, it's very difficult to move this backwards. Therefore, all chihuahuas are mammals. That's an AAA1 argument, if you remember that, what we did before the midterm. And we know that those are valid. So, but obviously, to do the first part, you have to introduce a name, and then you can do hypothetical syllogism. So you say, if A is, that is an A. No, actually, it's a U. Because the rule here is universal generalization can only generalize from the name U. This is my own rule. This is not in the book. I will explain this more in class, but basically this is my rule. You cannot do universal generalization from any name but the name U. The reason why you can do universal generalization from the name U here is because it's been introduced by universal instantiation. So so there needs to be another rule here, which is you can only introduce the name U by either universal instantiation or assumption. Remember assumptions? If you're doing a conditional proof or a reductio ad absurdum. So, you can only introduce the name U by universal instantiation or by assumption. Either of those ways allows U to stand in for anything in the universe. U is kind of generic. It could be anything. And because U is generic, I'll say more about this in class, you can universally generalize from it. Kermit is not generic. Kermit is a specific individual. And what is true of Kermit isn't necessarily true of everything in the universe. But we know, because we've already started from a general claim, that this is true of anything in the universe. So U can sort of be a dummy for anything in the universe, which is why you can universally generalize from it. All right. I'm going to talk more about this in class, but I thought this would be a good starter in case you wanted to finish your homework. That should give you an idea of when something is legitimate and when it isn't. If it follows all of the rules, the 2 rules for universal instantiation and existential generalization, the 3 rules for existential instantiation and universal generalization, then it's okay. If it violates any of those rules, then it's not okay. All right.